Good morning, everyone, and welcome to this lecture. And welcome to the next heading, next topic. Next heading or next topic is modern physics. Well, it is known as modern because that was added very recently. Even when we say very recently, that very recently is some 20-25 years ago or 30 years ago. There are other branch of physics which are more recent, quantum physics, and all those things which we don't study in 11th and 12th standard. But this branch is known as modern physics, and it starts with the first heading, and the first heading is atomic structure or structure of the atom. Now, this entire topic, atomic structure or nuclear physics, radioactivity, all these chapters are both part of physics as well as chemistry. So you might have done it in chemistry, you might not have done it in chemistry, doesn't matter. I will try to cover it in the most appropriate way. Atomic structure. Now, as soon as we go on to atomic structure, we know that every element consists of atoms, and every atom has a positively charged nucleus. Then we have electrons which are moving in orbits. Then we have inside the nucleus protons and neutrons. We know that's the case, but we'll just go back and see how this theory actually came into being, and we'll see the development of this. We will see the development of this, and we start with the first one. You might not have to note this, you just have to see what is this. The first one is the Dalton's theory. The Dalton theory. What did he say about the atom? Every material is made up of particles known as atom. Atom is indivisible. We still know that it is not. It cannot be subdivided. It cannot be created nor destroyed. All atoms of the same element are identical, whereas atoms of different elements are different. The atoms of different elements are made up of hydrogen atom. That is what he taught. The heaviest is 10 times, and the mass is about 250 times the hydrogen. The atom is stable and electrically neutral. As you can see, some part of what he said is correct, and not everything is correct, but yeah, some part of whatever he said is correct, as you can see. Do we understand this? So this was your Dalton's theory of structure of an atom. Now, we normally do not find many questions on this Dalton's theory, uh, but still just going through them quickly so that we get an idea of how this structure of atom came into being. Next theory, what was the next one after Dalton? Who came forward with the next theory? Not heard?
J.J. Thompson.
J.J. Thompson. J.J. Thompson was the next one who came up with his theory, and this was the Thompson's model of an atom. An atom is, as a whole, electrically neutral. Positive charge present inside a sphere is equal to the negative charge. So this is how the structure was according to Thomson's model. The shortcomings of Thomson's model: it could not explain the spectrum of atoms, and it could not explain the scattering of alpha particles. The scattering of alpha particles could not be explained by this model. So this was one of the older models, Thomson's model. You have heard about this, yes or no?
Yes, sir.
That was Thomson's model. Then after that came what?
Rutherford Goldfoil experiment.
Rutherford alpha scattering experiment, or the gold foil experiment, as it is known as in this what. So what was there in this experiment? Well, can anyone explain what was happening here?
Uh, 1 out of 10,000 alpha particles uh, is like reflected back with the 180 degrees angle, that is straight away back, and majority of the alpha particles have penetrated through the foil.
Right. So basically, alpha particles was passed through a small hole, and they were allowed to fall on a thin gold foil. They were allowed to fall on a thin gold foil. Most of them, was the arrangement. Most of them were able to pass through almost undeviated. Some of them were deviated by large angle, and about 1 in 8,000 particles, it went back at an angle more than 90 degrees, or approximately equal to 180 degrees. Do we understand this? This was what? This was
Rutherford's alpha particle scattering experiment.
experiment. And one more important diagram that you have to understand here is about the number of particles and about their scattering angle. I don't know if you have seen this diagram before. I will try to put this diagram together so that you can see this number of particles which are scattering. It depends on cos square theta by cos raised to the power 4 theta by 2, and this is the graph. Do not forget this. I have seen a lot of questions coming on this particular aspect. This theta is known as the scattering angle. Do we understand this?
Yes, sir.
This theta is known as the scattering angle. And how does the number of particle depend on the scattering angle? You may not draw diagram number 2. If I just name this diagram, this is diagram number 1. You may draw this. This is diagram number 2. You may not draw this. This is diagram number 3. You have to draw this to understand what is happening here. I hope you understand the meaning of the angle theta. Do you understand the meaning of the angle theta?
Yes, sir.
Okay. You also need to understand. You also need to understand this point, which is known as the impact parameter B. Do you see this B? This
Yes, sir.
impact parameter. This B is known as the impact parameter. So remember this. I'll give you 2 minutes to note this down. Remember, in the diagram, you have to know two things. One is the impact parameter B, and one is this R naught. Note down these two things. This is a very good diagram explaining everything that is going to be asked. Now, these are the observations that we have from the Rutherford scattering experiment. The first observation is most of the alpha particles go undeflected. Some of them are deflected through small angles. A very few, 1 in 1,000, are deflected by more than 90 degrees. Still very few are returned back. Distance of closest approach. Now, what do you mean by this distance of closest approach? Do you see that in the diagram, that distance of nearest approach? What is the distance? It comes nearest to the nucleus. Do we understand this? Did you draw it in the diagram? Yes or no?
Yes, sir.
This is R naught, and this is known as the distance of nearest approach. And this distance of nearest approach is 1 by 4 pi epsilon naught Z square by E, where E is the kinetic energy of the alpha particle, half mv square. Do not forget this in any point, in any case. The next thing that you must know is the impact parameter. This impact parameter, or B, is the distance of the velocity vector from the center of the nucleus when the alpha particle is very, very far away. What you have to remember here, you may not be able to remember this formula. You may also remember this formula. I mean, this is exactly same as R naught, similar to it is just multiplied by cot of theta by 2. I have seen a lot of questions come on this, on what all factor this impact parameter depend on, and most cases they ask with the scattering angle what happens to this impact parameter. So this yellow thing, whether it is in the lower blocks for impact parameter or is it in the upper block for the distance of closest approach, these are very, very important results that can make a hell lot of a difference in your final result. I'll give you 2 minutes to note it down. Then from this Rutherford experiment, we can make some conclusions. Since most of the alpha particles which are positively charged, they go undeflected. That means most of the mass and most of the positive charges is in a very small it's in a very small space, and that space came to be known as the nucleus. Do we understand this? The electrons are orbiting in the electrons are in outer orbits, and the maximum space inside the atom is empty. Do we understand this?
Yes, sir.
One more thing you have to understand is this relation, that is the relation between the thickness of the foil and the number of alpha particles scattered. I have seen questions come on this, and that is why I'm giving you all these formulae. N by T is a constant. So N is directly proportional to T. If you increase the thickness, the number of scattered particles become more and more. Do we understand this?
Yes.
These are the things that you have to note down. I'll give you 2 minutes to do it. Then we come to the drawbacks of this model. Remember, this chapter is more about remembering and how many ways and how many things and how many formulae you can remember, because there is no technicality here, there is no understanding of it. You just have to remember these things: theories, drawbacks, formulae, this, that, how you can write this, how you can write this, and all those things. If you can remember that, this chapter becomes very easy, and you can expect 2 or even 3 questions from this chapter in the entire exam, including physics and chemistry. And if I include the entire modern physics as a complete package, you can even have 5 or 6 questions coming, combining physics with chemistry, 3 or 4 questions in physics and 2 or 3 questions in chemistry. So this has potential of 6 questions, and all these questions and our answers to these questions are pretty simple, but you'll have to remember things, and I know that this is hard for you, but I can't help it. What were the drawbacks? The drawback was the stability. I mean, if an electron is accelerated, we know that when an electron is accelerated, it must emit EM waves. Yes or no?
Yes.
Now, if this emits EM waves, it will be emitting energy. If it emits energy, the the energy of this will become less and less. The speed of this will become less and less, and therefore it must eventually collide with the nucleus. But we know that that does not happen. Yes or no?
Yes.
Stability of the nucleus was a problem. It could also not explain the spectrum of atom, and we will see that spectrum. It could not explain the spectrum of the atom. According to the theory, the spectrum must be continuous, but the spectrum is not continuous. And it also could not explain why the electrons are orbiting outside the nucleus. It could not explain that. So these were the drawbacks of the Rutherford model, and what we could understand and what we could not understand. I give you 2 minutes to note this down. So after Dalton and Thompson and Rutherford model, you've seen all these three, comes the next one, and the next one is
Bohrs.
Bohr's atomic model, or Bohr's theory. And he proposed this theory, which is applicable for some lighter, which is applicable for hydrogen and hydrogen-like atoms. What do you mean by hydrogen-like atoms?
He plus.
Hydrogen-like atoms are atoms which has a
Electron.
single electron which is revolving around a nucleus of charge Ze, where Z is the atomic number of that element and E is the charge of an electron. Do we understand this?
Yes.
Now, this Bohr's theory is based on some postulates or some assumptions. The first postulate or the first assumption is whenever this electron is revolving in this, electrons are going to move in circular orbits. Do we understand this?
Yes.
These circular orbits, discrete circular orbits, are also known as stationary energy levels. We will see that. Now, when this electron is revolving in this circular orbit, they require this centripetal force for their motion. And who is going to provide this centripetal force? Who is providing this centripetal force for this electron?
Nucleus.
A single electron is moving in a circular orbit of radius r. Who is providing this electron with the centripetal force to move in a circular orbit? Is the electrostatic force of attraction between the positively charged nucleus and the negatively charged electron. This electrostatic attraction force is giving it the centripetal force. 1 by 4 pi epsilon naught ZE square by R square becomes MV square by R. So this is the first postulate. This is the first thing that you have to understand. The diagram is there. I hope you understand it. I'll give you 2 minutes to note this down. Now, as I said, the electrons can only revolve in discrete circular orbits. Electrons revolve in discrete circular orbits, and these are known as stationary orbits or stationary shells or stationary energy levels. Only those orbits are allowed where the angular momentum is nh by 2 pi. I hope you remember this. Yes or no?
Yes.
Where h is the Planck's constant and n is the number of orbit or the principal quantum number. Yes or no? When they're orbiting in this stable shell, they have a definite energy, angular momentum, and velocities. In these stationary orbits, they are not emitting any radiations, even though they are accelerated. And remember, in EM waves, I told you that even if an electron which is moving in in an atom, it is accelerated, it is not emitting any EM waves. Do we understand this? Electrons in the outer orbits far away have greater energy than the inner orbits. So electrons can obviously jump from the outer shell to the inner shell, and whenever they jump from outer shell to inner shell, they will always emit radiations, and that radiation will be in the form of electromagnetic waves or electromagnetic radiation. When they are in their stable orbit, stable energy shells, they are not going to emit any electromagnetic radiation. But when they jump from lower, they can always jump from higher to lower, because higher has more energy and lower has less energy, but they cannot jump from lower to higher. To move from lower to higher, they must be given energy. Do we understand this?
Yes, sir.
I'll give you 2 minutes to note this down. I hope all of you know this. Yes or no? No, yes.
Yes,
Now remember, the outer orbits have more energy, inner orbits have less energy. Whenever an electron and on its own can jump from higher energy to lower energy. When it jumps from higher energy to lower energy, it will emit a radiation. This is the radiation, and the energy of this radiation will be h into f. Do we understand this?
yes, sir.
But to make an electron to go from lower energy to higher energy, inner orbit to inner orbit to outer orbit, someone must have to provide it that energy. Same amount of energy has to be provided. Do we understand this?
Yes, sir.
I'll give you 2 minutes to note this down. Now let us move and try to get the formulae for the various things. The first formula that we are going to understand will be the radius of an orbit. Remember, all these formulas are derived from the basic equations, and we have already seen these basic equations. With these basic equations, using these basic equations, we derive all these formulae, and then the thing is, you will have to remember all these formulae in whatever different ways that you can remember. So the basic equation that you all know, this is equation number 1 and this is equation number 2. Eliminating different things between these equation, we can find out the radius of the nth orbit of hydrogen or hydrogen like nucleus, hydrogen like atoms, and the radius of this nth orbit is given by this formula, n square f square by 4 pi square k. Remember, k is 1 by 4 pi epsilon naught. Do we understand this? These
Yes, sir.
are, do we understand this? It's just an elimination that we have done, nothing else. We have just eliminated things from this. Do we understand this?
Yes, sir.
This is the first way of remembering this. R is n square h square upon 4 pi square k z m e square. I don't know if you can remember this. This is again equal to this one. If I convert it, the value of k into 1 by 4 pi epsilon naught, and when you put, because all of these are constants, when you put the values of all these constant, you end up with 0.53 or 0.529 n square by z in Armstrong units. Do we understand this?
Yes,
Now from here you must remember that this r is directly proportional to n square and inversely proportional to z. Do we understand this?
yes, sir.
Is it difficult for you to understand? Please tell me.
No, sir.
Everyone understands this?
Yes, sir.
So if I draw a graph between R and the principal quantum number, it would be like this. Yes or no?
Yes.
And if I draw a graph between R and Z, it will be rectangular hyperbola. Yes or no?
Yes.
Now you must also remember that this 0.529 is a very important number, or 0.53 is a very important number. Why it is a very important number? Because it is what? It is the radius of the first Bohr orbit of hydrogen atom. Do we understand this?
Yes.
Do we understand this?
Yes.
So remember, this 529 is also known as Bohr's radius. This 529, 0.529 or 0.53 is also known as the Bohr's radius, and the value of this Bohr radius is nothing but it is equal to 0.53 Armstrong unit, which is coming on your screens now. Do we see this?
Yes.
I'll give you 2 minutes. Take a deep breath. Note down these formulae very, very carefully. The next formula that we are going to see will be the speed of an electron in an nth orbit, and there are different ways in which you can remember it. The speed in the nth orbit is given by this formula or this formula. This is the way that I remember: C by 137. Where what is C?
Speed of light.
Speed of light. And if you do C by 137, you will have this 2.2 into 10 raised to the power 6 Z by N. Remember, this chapter is all about remembering the formulae in various ways. If you draw a graph between the speed of an electron in the nth orbit and the number of orbit, it will be a rectangular hyperbola. Do we understand this?
Yes.
Now this C by 137 is known as V naught, where V naught is the speed of electron in the first Bohr orbit. Do we understand this?
Yes.
Remember, beta, this chapter is all about this chapter is all about this chapter is all about remembering different ways in which you can remember the formula. If you can remember the formula, you can do a lot better things. Do we understand this?
Yes.
I give you 2 minutes to note this down. Then comes this revolutionary diagram which tells us the other things. The first one is angular speed, then frequency, time period, angular momentum, current, magnetic moment, and magnetic field. You may not be able to remember the formula in the second column, but you will have to remember the formula in the third column. What is their dependency on the atomic number and the principal quantum number. Do we understand this?
Yes.
This 6.62 into 10 raised to the power 15, you can call it T naught. What do you mean by T naught? Ah, not T naught. You can call it F naught. What do you mean by F naught? What do you mean by F naught? F naught means the frequency of an electron orbiting in the first Bohr radius of hydrogen atom. You can write this as 1.51 into 10 raised to the power minus 16. This is time period, so it becomes the reverse. This 1.51 into 10 raised to the power minus 16 can be called as T naught. What is T naught? Well, T naught is the time period of revolution of an electron in the first Bohr radius, first Bohr orbit of a hydrogen atom. The other things are there. The only thing that you can do is that you remember them. That takes us to the next most important concept, the concept of energy. Now, this electron is moving around a positively charged nucleus. It has two types of energy. What are the two types of energy? One is the electrostatic potential energy, which is given by this formula. Because of a positively charged nucleus, it has electrostatic potential energy, but this electrostatic potential energy would be negative because one charge is positive and the other charge is negative. Do we understand this?
Yes.
Then it has kinetic energy because this electron is moving with a certain velocity v. Yes or no? And you can see this kinetic energy is potential energy divided by 2. Modulus of potential energy divided by 2. Do we understand this?
Yes, sir.
So when you add these two, you will get the total energy. Now you can remember this total energy in different ways. This is the first way of remembering it. Remember, this chapter is all about remembering things in different ways. This is the second way of remembering it, where Rn has been substituted by its value. What you have to understand is the value of this thing. Now remember, this thing that comes over here, this entire thing that comes over here is actually known as R, which is the Rydberg's constant. Do we understand this? This
Yes.
chapter, as I keep on telling you, is all about remembering things in different ways. You can write this as RHC minus RHC into Z square by N square. Again, this minus RHC, the value of this minus RHC becomes minus 13.6 electron volt. Have you heard this? Minus 13.6 electron volt.
Yes, sir.
You have 2 minutes to note this down. Now, some points that you have to remember, understand. Each Bohr orbit will have a definite energy. For hydrogen atom, Z is 1. Energy will be minus 13.6 divided by N square. We all understand this.
Yes, sir.
This RHC is known as the Rydberg's energy, which is actually equal to 217, 2.17 into 10 to the power minus 18 joule, which comes equal to 13.6 electron volts. Do we understand this?
Yes, sir.
Total energy is the negative of kinetic energy. It is the potential energy divided by 2. Yes or no?
Yes, sir.
Last but not the least, if orbit is at a distance of infinity, very far away from the nucleus, the energy of that orbit will be 0. Yes or no?
Yes, sir.
And that is the highest possible energy. Do we understand this?
Yes, sir.
That takes us to the next set of definitions, if you want to call them definition, or next set of points. The first is ground state. You know what is the meaning of ground state?
Lowest possible energy state.
Excited state. N is equal to 2 is known as the first excited state. Yes or no?
Yes, sir.
Ionization energy. Energy required to move an electron from ground to infinity. Yes or no?
Yes, sir.
For hydrogen, the energy required for hydrogen-like atoms, the energy required to move an electron from ground state. to infinity will be minus 13.6 z square. If you want to remove the electron from any other state to infinity, you will divide it by n square. Do we understand this?
Yes.
Ionization potential is the potential you require to raise it. So it is ionization energy divided by the charge of an electron, because energy is E into V. Do we understand this?
Yes, sir.
So the ionization potential of hydrogen atom, because its ionization energy is 13.6 electron volts, its potential becomes 13.6 volt. For helium plus, it becomes 54.4. I hope everyone understands this. Yes or no?
Yes, sir.
That takes us to the next heading, and the next heading is binding energy. Have you heard this term, binding energy?
Yes.
And energy required to move an electron from any state to infinity is known as binding energy. You need that much energy to separate the electron. Do we understand this?
Yes.
Excitation energy to move an electron from ground state to any other state. Excitation potential will be the potential required to do that. If the excitation energy is 10.2 electron volt, the excitation potential will be 10.2 volt. We understand this, yes or no?
Yes, sir.
Then we come across this simple diagram which tells us about the principal quantum number. Do we see it here?
Yes.
In terms of orbit, this is the first, this is the second, third, fourth, and so on. This is the energy of hydrogen atom. This is the energy for hydrogen like atom multiplied by Z square. These are the ionization energy. I hope everything is clear. Yes or no?
Yes.
Just to just for you to understand how these things are. Give you 2 minutes to note this down if you want. Then, sir, then we move on to this question. Let's see if you can solve this. The first excitation potential of an hypothetical hydrogen-like atom is 15 volt. What do you mean by first excitation potential? This is how questions would be framed. What do you mean by the first excitation potential?
Sir, potential needed for the
For the
electron
electron to move from
ground to first excitation state, first excited state.
ground to first excited state. Do we understand this?
Yes, sir.
Then what would be the third excitation potential? Second excitation potential is from ground to n is equal to, ground is n is equal to 1. So the first excitation potential is from n is equal to 1 to n is equal to 2. Do we understand this?
Yes, sir.
This is from n is equal to 1 to n is equal to 4. Do we remember this? Do we understand this? You have 2 minutes to give me the answer. So how are we supposed to do this? So the first excitation potential is given as 15 volt. So what is the first excitation energy? What is the first excitation energy? When I talk about the first excitation energy, that would be the energy required to move this electron from n is equal to 1. First excitation energy, let me call it as delta E1. First excitation energy will be energy in the second level minus energy in the first level. I hope you understand this. What would be the energy in the second level for this hydrogen-like atom? It would be minus 13.6 into Z square by n square N is 2, 2 square is 4. So energy in the second orbit of this hydrogen-like atom would be minus 13.6 Z square by 4. Energy in the ground state would be minus 13.6 Z square by 1. E2 minus E1 is given as this. Yes or no?
Yes.
Now, from there you can find out lots. Remember, what you should remember. You have to do this question in the easiest possible way. Yes or no? Let me call this E1 as E0. So this E2 will become E0 by 4. Yes or no? You'll have to remember all these formulas and that will make your life easy. So if one is E0, we always call the ground level as E0. The first excited state will become E0 by 2, E0 by 4. The second excited state will become E0 by 9. The third excited state will become E0 by 16. So here I can write E0 by 4 minus E0 is given as 15 electron volts. Yes or no?
Yes, sir.
From here I will get 3 E0 by 4 negative sign will be equal to 15 electron volts. Then I move on to the next part of the question. In the next part of the question, I am given the third excited potential. From there, I can find out the third excitation energy, and the third excitation energy will be the energy required to move it from first to the fourth orbit. Yes or no?
Yes.
To get the value of E4, this E4 will be equal to E0 divided by 16. Yes or no?
Yes, sir.
So E0 by 16 minus E0, this is what you need to calculate. The answer would be in electron volts. Now this E0 by 16 minus E0 is simply minus 15 by 6 into E0. From here, you should be able to calculate the energy difference. The energy difference will come in electron volts.
18.75.
From there, you will get the value of voltage. So the excitation voltage or excitation potential, the third excitation potential, the answer that I have is 75 by 4. I love fractions, and that is why I will call the answer in fraction. 75 by 4 volt would be the excitation potential. Did you get this answer?
Yes, sir.
Well done then. You have to understand all the questions are to be done in this similar way. I'll give you 2 minutes to note it down. That takes our attention to what happens when an electron moves from higher orbit to lower orbit, or it is given energy to move it from lower orbit to higher orbit. Now, electron can move from higher orbit to lower orbit if there is a vacancy in the lower orbit, and we will see in the next chapter how this vacancy can be created. So if there is a vacancy in any of the inner shell, an electron from the higher shell can jump and take its position. Yes or no? Yes or no?
Yes, sir.
Then always there will be a photon or electromagnetic radiation of frequency f emitted. Do we understand this? Whenever an electron on its own jumps from higher to lower orbit, or it is made to jump from a lower to higher orbit, there is always energy emitted in the form of electromagnetic radiations or photons. How much energy is liberated or radiated, that is equal to the difference between the two levels. Do we understand this? Do we understand this? Do we understand this? Not getting
Yes.
your voice. And you can write it in this fashion. We get this?
Yes.
This is the energy of the photon. To find out the frequency of the photon, this is the formula for frequency of the photon. Remember, it is directly proportional to z square. I hope everyone is making notes. Remember, I have told you all these. This chapter is completely about remembering the formula. Yes or no?
Yes, sir.
This is the wave number, or one by wavelength. This is the wave number, one by wavelength. Do we understand this?
Yes.
Or 1 by wavelength. This is the number of spectral lines. How many lines are emitted or can be emitted? We will see questions on this, don't worry. Now, when this electron is emitted, photon is because of the transition of electrons, photon is emitted, the atom recoils. This is the question that will come in JEE Advanced. The recoil momentum of the atom is same as the momentum of photon, and it is h by lambda. So you multiply 1 by lambda by h and you get this. The energy of the recoil energy of the atom will be p square by 2m, where m is the mass of the atom. Note down these formulae very, very carefully. Try to read them and then write them, because all these formulas are not formulae. They are potential questions that are going to come. I'll give you 2 minutes to give me the answer. And this is the first question, sir. The ratio of areas within the electron orbit for the first excited state, the ground excited state for hydrogen atom is. And the answer is 16 is to 1. Why is the answer 16 is to 1? You must remember that the radius of the Bohr orbit for hydrogen atom, remember, for hydrogen atom, Z is 1 and it is constant. So it is inversely proportional, it is directly proportional to n square. Yes or no?
Yes, sir.
Area is proportional to r square. Yes or no?
Yes, sir.
So A1 by A2 will be equal to R1 by R2 whole square. That will be equal to N1 by N2 raised to the power 4, 2 raised to the power 4, and the answer becomes 16 is to 1. Everyone understands this? Yes or no? No, yes.
Yes.
Everyone understands this?
Yes, sir.
This is the next question. The innermost orbit of an hydrogen atom has a diameter of this. What is the diameter of the 10th orbit? Well, it again depends on the simple fact that R is proportional to n square. R10 divided by R1. R1 means the ground state. That will be equal to 10 by 1 whole square. And the answer simply becomes whatever is the ratio of radius, same will be the ratio of diameters, and the answer is 106. 106. 106. 106. Armstrong units. Do we understand this?
Yes, sir.
Here comes the next one. In the Bohr model of the hydrogen atom, if R, V, V is not V, it's mu, that is frequency, and E energy represents, and E represents the radius, the speed, so V is the speed, and E is the total energy of the electron, respectively, which of the following quantities is proportional to the quantum number n. Here is a small correction. This r is not the radius of the orbit. This r is actually your Rydberg's constant. This r is your Rydberg's constant. So just correct it and now solve this question. This r is the Rydberg's constant, not the radius of the atom, radius of the orbit. Option B, I'm afraid, is the wrong answer. Well, you just have to remember what is the Rydberg's constant. The Rydberg's constant, the velocity, as I told you, this chapter is all about remembering. So this one is your Rydberg's constant, this is your velocity, and this is your total energy. What is proportional to n? You have to remember what is proportional to what. I had given you. You cannot remember all these things because dimensionally you will have to find out their things dimensionally. But if you can remember this table, the table that I gave you, this one, you remember what is proportional to what? Z square n cube, Z square n, Z by n. From there you can see which factors are going to cancel. You forget about that constant terms. You just have to look at what is proportional to Z and in terms of n. And if you could remember that, you could see very clearly that this R Rydberg constant is proportional. No, this is not R. This is the, I think, radius of the orbit. Yes or no? Not the radius, because Rydberg's constant is a constant. It cannot be proportional to n. So this must be the radius of the orbit only. This is the formula for the radius of the orbit. The radius of the orbit is proportional to n square by c. The velocity is proportional to z by n, and energy is proportional to z square by n square. It cannot be Rydberg constant. It has to be the radius. So now you can see which will be proportional to n, and if you just multiply, you will see that v into r will be proportional to n. Do we understand this?
Yes, sir.
This is how you must do any question which comes. There was a mistake here which I committed. I thought that capital R would be the Rydberg constant, but capital R is not the Rydberg constant. It is the radius of the electron. Rydberg constant is a constant. It does not depend on n and z. N and z cannot come there. Do we understand this?
Yes, sir.
So if any question comes in this category, this is how you must be solving that question. Did you get this?
Yes, sir.
Here comes the next one. It's important for you to do as many questions as possible from these sets. I will try to do the maximum number possible, including the question that has come in your attempt that you already have given. I've already sent you a sheet, and I'll prove that whatever comes in that sheet comes in the JEE mains as well. This is the next one. Option A, sir, we must understand that energy for any hydrogen-like atom is proportional to Z square by N square? Yes or no?
Yes, sir.
So, energy in the helium divided by energy in the hydrogen, the orbits are same, so it is proportional to Z of helium divided by Z of hydrogen squared. So the answer simply becomes 4 times En. Do we understand this? Yes or no?
Yes, sir.
Everyone understands this? Yes or no? You understand this?
Yes, sir.
This is the next one in your horizon. Energy of an electron in the nth orbit of hydrogen is given by this formula. The formula may not be given. The amount of energy required to transfer the electron from the first to the third orbit is. Remember, same question can come in the coming sessions. So basically, you need to transfer an electron from the first to the third orbit, lower to higher energy level. So you need energy. How much is the energy you need? Is the difference in energies, that is simply equal to energy in the third orbit minus energy in the first orbit. So the energy you need is minus 13.6 divided by 3 square is 9 minus of 13.6. Yes or no? No, yes.
Yes.
You must remember all these values. What is the energy required to move it from first to second, first to third, first to fifth? In fact, in that table, if you remember, see, that's the faida of doing hard work. If you do hard work correctly, smart hard work, if you remember this is this one and this is this one, you just subtract the two and you get your answers. Yes or no?
Yes, sir.
You must be smart. If you do your homework correctly, if you do the things that you have to prepare beforehand correctly, well, you can solve the questions that are going to come pretty easily. This is a question that appeared in one of the previous JEEs. It was known as IITree back then. If the binding energy of an electron in the hydrogen atom is 13.6, they might not give you that. The energy required to remove the electron from the first excited state of lithium 2 plus. Option B 13.6. Remember, for any hydrogen like atom, it is minus 13.6 Z square by N square to remove the electron from the first excited state. So first excited state means N is equal to 2. The positive of that energy would be the binding energy. Yes or no?
Yes, sir.
So minus, so let me write it in minus as well because I'm talking about energy. So minus 13.6 divided by 4 multiplied by lithium 9. Just have to multiply and divide, and you can understand that it cannot be 13.6, it cannot be 3.4, it cannot be 122, it has to be 30.6. Do we understand this, or this has gone above our head? Saying bye bye.
That's true.
And remember, this is the fruit of hard work. Now let me present to you a question from the session that you have given. This is a question taken from the session of 31st Jan, shift 2. I don't know how many of you were there in that session. And this is the question that appeared. As you can see, it is just a manifestation of the question that we have done. In fact, the question that we had done was tougher than this one. Find ionization and energy of second excited state of
Option
lithium
4,
2.
13.6.
Option 4, 13.6. Do we understand this? How it is simple? See, JEE
Yes.
is so simple. If you just do it in the correct way. I will be doing question from your previous session as well, so don't worry. Now this is again a question from one of the previous sessions. Let me see if I can tell you which session is this. I don't know which. This is from shift 2 of some session. I don't recollect. Maybe this is 30th of Jan, shift 2. And let's see if you can do something with this. A photon is emitted from something something, and then you have to find out something something, and I hope you can do that something something. So how are we going to get this? Remember, the difference in energy is delta E. That will be equal to energy at the fourth level minus energy at the first level. That should be equal to, you have to find out the corresponding wavelength, yes or no? That should be equal to h into f, and this h into f is h into c by lambda. Do we understand this?
Yes, sir.
So from here you can find out this lambda, and remember this formula. This is hc divided by delta E. Hc divided by delta E, and this Hc, the value of this Hc is given as, the value of this Hc is given as 1240 nanometer electron volt. So if you put the energy in electron volt, the difference in energy is in electron volt, you will get lambda in nanometers. So what is the difference in energies? What is the difference in energies between the fourth level and the first level? Yes or no? Do you know that? How much is the difference in energy level? How much is the difference in energy level between the fourth level and the first level of hydrogen atom? Hmm? No one knows it? Anyone knows it? I don't think anyone knows it. It is equal to 12.75 12.75 electron volts. E4 minus E1. So your lambda, the wavelength becomes 1240 divided by 12.75 in electron volt. So the answer that you are going to get would be somewhere in the range of, no, how it can be this one? 1275. Somewhere in the range of 97.3 nanometers, and that is the answer that we were looking at. Please note down this question. Well done, sir. Then that brings us to an end of this class and this session. In this session, we have completed almost the entire aspect of structure of atoms, starting with the Dalton theory to Thomson, so the Rutherford experiment, and right now we are in the Bohr theory. In the next class, we will be winding up this chapter with all the questions that have come and possibly can come in the next session. We will be also seeing the drawbacks of the Bohr's model. We will be seeing the hydrogen spectrum and the other things. So I'll see you tomorrow. I'll give you this time so that you can go back home and try some more questions from the sheet that are already there with you. Remember, the more the number of questions that you are going to do, the more is the probability that same or similar question, exactly same, is going to come in the session that you are going to give. So take care and God bless you. Bye bye. If you have any doubts, please come up.